There's only fun if people like I go into you see like a progress capture. For that, like, what's about
all right, I think we'll get started despite the fact that nobody's here. Yeah. All right, so where we left off last time, we were talking about Gauss's law, and what we showed is that this integral of E dot dA around a closed surface had to be equal to Q enclosed over epsilon naught. And then we could use the divergence theorem to re-express that same result in differential form. And so that led to two forms of Gauss's law. And then we also considered the path integral of the electric field around a closed loop. And we found that that was zero. So in mechanics, we would say that means the electrical force, which is Q times E, would be a conservative force because it's path independent. If you go around from A to B, doesn't matter how you go from A to B, the result of that integral would always be the same. So in particular, if you let your starting and ending points on your path be the same point, you do some closed loop, and again, it doesn't matter how you take that loop. As long as you get back to your starting point, that integral will evaluate to zero. And then we could take Stokes' theorem and show that that's equivalent to saying that the curl of E had to be zero. So this, as far as I know, this second set of expressions doesn't really have a name, but they are part of the Maxwell equations. So what I want to do today is I want to start talking about electric potential. And the reason we're going to do this is because we've now come up with a couple of ways to calculate electric fields from different charge distributions. One was just to integrate over the charge distribution and basically use the result for the electric field of a point charge, and then consider all these little volumes in our big, larger piece of charge object act as point charge, and we add up the contributions from all those little pieces to get the total electric field. That could be, in general, a pretty hard calculation. So we then developed Gauss's law. Gauss's law gave us a way to find E when we have highly symmetric distributions of charge. So spherical charge distributions, planar charge distributions, and linear charge distributions. What we're going to try to do is we're going to come up with a third way to help us calculate electric fields, and that will be by first finding the electric potential, which, because it's going to be a scalar quantity, is in general a little bit easier, and then we'll be able to then deduce the electric field by taking a derivative of that electric potential. So to start, I just want to consider this integral of E dot dl. So that's a line integral, and what we'll do is we'll integrate to some position R, where we're going to start from some origin O. So this is just some reference point. It's arbitrary. So this is some arbitrary reference point. Okay. Now, when I actually evaluate this integral, what it's going to depend on is the upper and lower limits of that integral. So in particular, it will depend on our ending point, this vector R, So whatever the result of this is going to be, it's going to be some function of r. And I'm going to call that function v because it's going to be our electric potential. And I'm going to add one other thing here. I'm going to put a negative sign, and that's just by convention. So this negative sign is by convention. Spell that right. Then maybe I did, I'm not sure. Okay, and then this is just a function of the ending point r. Okay, so if that's true, then it must be the case that if I was to evaluate the integral from some reference point to a, then that would be equal to minus whatever this function is evaluated at the point a. I'm just going to move the minus sign over to the integral here. Okay, so I just multiplied all of this by a minus sign, and I replaced the r with an a. And of course, I could pick a different point, and I could say, well, VB is minus the integral from some origin, some reference point to b of E dot dl. All right, so what I want to do is I want to take the difference of these two. I want to take VB minus VA. So therefore, this change in V, whatever it is going to be VB minus VA. All right, and so that's going to be minus the integral from some origin to B of E dot dl. And then it would be minus the integral from some origin to A of E dot dl. But I'm gonna flip the integration limits, and I can do that as long as I flip the sign in front. And so this would be from 0 to sorry, I gotta flip the, I said I was gonna flip the limits. So my A is gonna be over here, and then my reference point is up here, and then we have a E dot dl. Okay, but then if you look at this, this says like integrate from O to A B, and then from A to O. Well, I could just combine those two integrals, right? It's better to think of going from A to O and then from O to B. Yeah.
So why do you just put limit? Because isn't negative of a negative integral? So you already have a positive?
Oh, sorry. Yeah, you're right. Actually, you are actually right. I did want to flip the limits, but I actually wanted to put the minus sign here. So you're right. There's 3 minus signs, right? Because we're going to start with minus, then we're going to flip, which makes it plus, but then we're taking the difference, so it gets minus. So yeah, you are correct. All right, good. So then that means that this V at B minus V at A is equal to minus, I'll factor that minus sign out now. Well, it's just the integral from E dot dl from A to B. In fact, I don't even need this bracket. So now I can combine those two integrals. Okay. So this is the change in electric potential when we move through an electric field E from an initial point A to some final point B. Okay, but we could take this a little bit further. We could say, well, if we wanted to, we could write this difference in V in another way. So from the fundamental theorem of calculus for gradients we know that so remember what the fundamental theorem does for us is it takes the integral of a derivative and expresses it in terms of just the values of the function at the two boundaries. And so in this case, the derivative that we're going to consider is the gradient of v integrated dot product with dl, and we go from a to b. So here's two expressions for the same thing, the same difference in v, and so these must be equal. No, not yet. So you're right, this one does not have a negative sign and that one does. So the only way that these two are equal, it's the same integral. So this gradient of v must be equal to minus the electric field. And so therefore, or another way to say it is E is minus the gradient of the potential. So this is the electric field expressed in terms of a scalar function. What maybe I should say in terms of the gradient of a scalar. And so the reason that this is going to be useful for us in a practical sense is if we can find V due to a charge distribution, whatever it is, it could be point charges, a line of charge, any complicated distribution of charge, then we can deduce E from minus the gradient of that potential. All right. And what we'll try to do, we'll do an example today where we're trying to demonstrate that calculating these potentials is in general easier than calculating electric fields directly. Okay, so that's going to lead us to Poisson's equation and the Laplace equation. We already know that there is a Laplacian, so we're going to assume that the Laplace's equation is going to involve the Laplacian, and it will. So if E is equal to minus the gradient of V, then what we could do is we could take the divergence of E, which is equal to rho over epsilon naught. Right, that's Gauss's law in differential form. But then if I just substitute in here minus the gradient of V, we would end up with, therefore, minus the divergence of the gradient of V is equal to rho over epsilon naught, and the divergence of the gradient is that Laplacian. So this is del squared. V is, I'm going to take the minus sign over to the other side, rho over epsilon naught. This is Poisson's equation. And I suspect that it's actually will be in the next chapter when we'll use this a little more. So just keep this in mind for when we get to chapter 3, hopefully pretty soon. So then Laplace's equation is really nothing different. It just says if we're in a region of space where there is no charge density, rho is equal to 0, so this is a charge-free region, then it's obviously just the case that the Laplacian of V would have to be equal to 0. Del squared V is equal to 0, and this is Laplace's equation. Okay, good. So what I want to do is I want to start to calculate some actual potentials. And we're going to start the same way we start every problem like this, is we're going to consider the simplest possible case of just a single point charge. Okay, and so this I may want to keep for later, we'll see. Okay, so let's consider the potential V of a point charge. Okay, so we know something about point charges already. We know that for a point charge, E is just these constants 1/4πε0, and then it's just Q over R squared in it. The electric field is going out radially from that point charge. So then, like, we could just calculate a potential directly is equal to minus some reference point to some R of E dot dl. Now, what we can do is the reference point is completely arbitrary. But what we need to do is we need to pick a value for this potential at some point in space. And when it's possible to do so, a good convention is to select the potential to be 0 when we're infinitely far away from the source of charge. There's a limitation, we can't always do that, right? Because if you had like an infinite sheet of charge, then, you know, even if you go out to infinity, the sheet is still around you. And so it doesn't make sense in that case to say, go to infinity and the potential is 0. But when you're talking about finite charge distributions or point charges, this is a good convention to adopt. So this reference point is arbitrary. It is convenient to define V at infinity is equal to 0 for point charges and other finite charge distributions. So that's what we're going to do. We should just keep in mind that we've done that, because everything that follows from this will be valid for selecting the potential of 0 at an infinite distance from a point charge. Okay, so let's think about this E dot dl. We've written down here that the electric field is radial. So when I take a dot product with dl, it's only the radial component that's going to survive, right? So if we're in spherical coordinates, we'd have like an r hat term and a theta hat term and a phi hat term. But I'm only going to care about the r hat term because of this dot product and the radial electric field. So it's going to be 1/4πε0 Q over, let's see, I'm going to put r prime here and dr prime just to distinguish our integration variables from our integration limit that we're going to use. Okay, fine. So then this potential is minus this line integral, so we get the minus sign. Q and 4πε0 are all constants. and we go from our reference point, which we're gonna say is infinity, and we go some distance away to r, and then we have dr prime over r prime squared. Okay, so this is r prime to the -2. When we integrate, we raise the exponent by 1 and divide by it. That's going to get rid of our minus sign. So we'll have a q over 4 pi epsilon naught. The r prime, 1 over r prime squared becomes 1 over r prime. And then we got to evaluate from infinity to some final position. Okay, good. So this is equal to q over 4 pi epsilon naught, and let's see, it's 1 over r minus 1 over infinity, and that infinity, the inverse of infinity is 0, and so therefore we get our results that for a point charge, this potential is equal to 1 over 4 pi epsilon naught q over r. This is with v equals 0 at r goes to infinity. So this is probably a familiar result that you've seen before. Remember, the only difference, it's kind of reminiscent of the electric field, except there are differences, of course. One is that this is a scalar function, so there's no direction, no like r hat or whatever. And instead of 1 over r squared, this goes as 1 over r. So let me add a page here. No, I wanted to add a page. Why don't you? Okay. So in this drawing here, what we've assumed is that we have a point charge sitting at the origin. And then we're finding the potential at some position over here. So here's r and here's v of r. Now, it's not always the case that our charge will sit at, sorry. Our charge won't always be sitting at the origin, right? So if q is not at the origin, we would have a drawing something like this. So I don't need to label these axes. So we would have, say, for example, here's q, and maybe I want to know the potential at this point. So here's our r vector, here's our r prime, and then this is our script r is r minus r prime. So in this case, what matters is the distance from your source charge to what Griffiths calls the field point. And so then when q is not at the origin, the potential would be equal to 1 over 4 pi epsilon naught q divided by the script r. Okay, good. So
would always be valid to write it with that, right?
yeah, it would always be valid to write it as that, because if q was sitting at the origin, then r prime would be 0, and then script r and r would be the same. Yeah. Okay, so electric potential due to many point charges. Okay, well, what we would do, I probably won't write it down, but we could just do this calculation for E is equal to a sum of the electric fields due to a bunch of point charges. And then we could just re-express, we could distribute the integral, so instead of an integral of a sum, we'd have a sum of integrals. Every single one of these integrals would evaluate to the same sort of expression. You would just have like a Q1, R1, a Q2, R2, Q3, R3. And so the potentials would just add up directly. So the electric potential also obeys the superposition principle. So therefore, this would be 1 over 4 pi epsilon naught, and then you just have this sum of qi over ri. Maybe I'll use this script r to be more general, so that we don't have to have all of our point charges sitting at the origin. All right, and then we'll do the same thing we did for electric fields. We'll say, well, if I had like Avogadro's numbers of charges on a sphere or something like that, I don't want to add up, 10 to the 23 different values. So what I'm going to do is I'm going to consider that object as having a continuous charge distribution. And so we just have to re-express the sum as an integral. So for a continuous line of charge, we would say the charge of an element of that line would be the linear charge density lambda times a small length of that line. For a continuous surface of charge, dq would be the surface charge density times some little captured area. And then for a volume of charge, dq would be the charge density times a little volume element. And so we could replace the qi's with these dq's and the sum with an integral, and that's how we would do a continuous distribution of charge. Actually, maybe we'll do this picture so that we can move on from it. So in that case, for a linear distribution of charge, the 1 over 4 pi epsilon naught is going to be the same. The sum becomes an integral. Q becomes dq, which is lambda dl. And then we have our script r. And then this would be dl prime. So script r, remember, is the distance between the source and the observation point. And the reason why lambda has been labeled with r prime is because that r prime tells us the position of the source of the charge relative to the origin. Okay, and then you'd have analogous things for surface charges. dA prime, and for volumes, rho r prime, script r, d tau prime. We just have to keep in mind that all of these things, because they rely on the electric potential of a point charge, all of these expressions assume that V at infinity is 0. Okay, I'm just going to go blow my nose, and I'll be right back, and then we'll do an actual example. Okay. All right, sorry about that. So here's the example I want to do. I want to find the potential due to a uniformly charged disk. Uniformly charged disk of radius r for a point, a height z above the center of the disk. So that's a mouthful. I'll draw it. So what we would have is like a disk, and then maybe our coordinate system is something like x, y, z. And we're going to have a point that sits here, and I want to know the potential at that point where it's a height z above this axis. We'll make our disk have radius capital R. The reason we're doing this example is because in tomorrow's tutorial, you're going to find the electric field at this point P. So what we'll do today is we will calculate the potential, then we'll take the gradient of that potential, and we'll find the electric field. And then tomorrow, when you do this example, you'll do a direct calculation of the electric field, and you should get the same answer. Okay, so how are we going to do this? What we'll do is we'll pick a little patch of area here. So there's my little patch of area. This has a charge dq, is the charge per unit area times sigma. Sorry, what am I doing? Sigma is the charge per unit area, so we have to multiply by the area. All right. Well, let's think about this a little bit. This is a distance r out to this little patch. Let me draw a top view of this thing. You keep coming back, don't you? Okay, so let me draw the top view. So if we're looking from above, we would have, say, our two axes, and then we'd have our disk, and then we're going to go out to some patch of area like so, and we'll say that this angular displacement is d phi. This is a distance r from the z-axis, and then this distance is dr. So the area of this patch dA is r d phi gives the lengths of these arcs, and then dr gives the lengths of the side, and so r d phi dr is the area of the patch. Okay, good. So the other thing that I'll draw on this diagram is that the distance from this patch to our point P is r squared plus z squared square root. So this is r squared plus z squared square root. And so I think that's all of the things that we're going to need to get started on this calculation. So let's see. V is going to be 1 over 4 pi epsilon naught, the integral of the sigma over the script r well, where was it? It was right here, like just times dA, right? Okay. So 1/4 pi epsilon naught. Now, this little script r is exactly this thing. It's the distance from the source to the point P. So it's square root of r squared plus z squared. So it's the integral of 1/the square root of r squared plus z squared. The dA we already wrote down was r d phi dr, and then we just had sigma. Okay. So let's see, that's going to be 1/4 pi epsilon naught. The integral of phi is 0 to 2 pi d phi, because we have to integrate around this entire disk. If we did that integral around the entire disk, what it would do is it would find the contribution of the potential due to this ring. And then after we do that, we would do the integral from r goes from 0 out to the full radius, capital R. So then we'd have also the integral from r is 0 to capital R of, let's see, well, whatever's left. We have a sigma dr over, I also have an r. I have sigma r times dr over the square root of r squared plus z squared. Okay, so let's do this calculation in full. This is not a hard integral to do. So what we could do is we could do a substitution. U is r squared plus z squared, so that du is going to be 2r dr. Z is a constant. The point P is just a fixed distance away from our disk. When when r is equal to 0, u is going to be equal to z squared. And when r is equal to the big radius capital R, u will be r squared plus z squared. Okay, so that means that our potential is going to be 1/4. Well, we can do this first integral. That's just going to be 2 pi. So 2 pi divided by 4 pi is 1/2. So it's 1/2 epsilon naught. And then it's the integral of u equals z squared to r squared plus z squared. Sigma is a constant, so let's just put the sigma out here. R dr is du divided by 2. So we get 1/2 of du. And then r squared plus z squared is u, so we get square root of u. So I could do this as u to the minus 1/2 du. Okay, good. Right. So let's see, when we evaluate the integral, we raise the exponent by 1, so it becomes plus 1/2 divided. So I guess we get a plus 2, which is going to cancel with this 1/2, I think. And so this is sigma over 2 epsilon naught, u to the 1/2 from z squared to r squared plus z squared. And then if we've done this correctly, which it looks like we have, we get v is equal to sigma over 2 epsilon naught, the square root of r squared plus z squared minus z, like so. And we can check that it has the right sort of features. The kind of feature that we would expect is we've always set so far the potential to be 0 when we're infinitely far away from the source. So if we set z equal to infinity, we get r squared plus z squared if this is infinity, that's just gonna be z squared, square root is z. And so we'll get z minus z, and so it goes away, it vanishes at v goes to infinity. So that's a good sign. So we can now find E using E is equal to minus the gradient of the potential. Now in cylindrical coordinates, your gradient is going to have derivatives with respect to r, with respect to phi, and with respect to z. But there's no little r's in this expression, it's just capital R, which is constant. There are no phi's in this expression. The only non-zero derivative is going to be the z derivative. And so this is going to lead to the z component is minus dv dz. And so that's what we have to evaluate. So since there's no phi or r dependence in v, we're just calculating the z component. Okay, so Ez is equal to minus d by dz of, well, it's sigma over 2 epsilon naught, and then what's in here, square root of r squared plus z squared minus z. Okay, so we get minus sigma over 2 epsilon naught. Let's see, what's gonna happen here? We're gonna get a 1/2, and the square root's gonna go to the bottom, and then we're gonna pick up a factor of 2z from the chain rule. So the 2z and the 1/2 cancel. So we'll get z over the square root of r squared plus z squared. And then the derivative of the next term z is just 1, and there's a minus sign. Okay. So fair enough. I think what we could do is we could say therefore E, the vector E, is only going to have a z component. So there'll be a sigma. I'm going to pull the z out over 2 epsilon naught. So sigma over 2 epsilon naught is there. I'm going to take this z outside, and I'm going to bring the minus sign inside. So if I take a z outside, I have a 1 over z here. And if I bring in the minus sign, it becomes plus. So it's 1 over z minus 1 over the square root of r squared plus z squared. And this is, and because I wrote it as a vector, I'll put in the direction, which is in the z hat direction. This is the electric field above the center of a uniformly charged disk. So in tutorial 3, you'll do this calculation in a different way, but you should get the same answer. The way you're going to do it is you're going to say, all right, let's start by calculating the electric field due to a charged ring. And I'm going to sit a distance z above the center of the ring. And so you do that calculation, and that's fine. Then what you do is say, okay, I can construct a disk by taking a bunch of rings of different diameters and adding them together. And you'll do that using an integral. And then you can get the electric field of that charged disk, and it should look like this. All right. I'm hoping that when you do that, you will find that what we did in class is easier. And it's easier because when I wanted to know the net potential here, I just add them up from all these different little patches of area, but they're just all scalar, they're all scalar contributions. So I don't have to find like only the vertical component. which you will have to do when you're doing the electric field calculation directly, because this little patch will make an electric field that points in this direction, but one over here will make it point in that direction. It's only the vertical components survive. Okay, good. So maybe let's talk about this picture so we don't have to keep moving it. This is kind of a nice picture from the Griffiths textbook. So this is just directly from the textbook. What they're trying to show is that you really, in electrostatics, have three sort of key variables, and they are like some distribution of charge that's been denoted in this drawing as rho, volume of charge, but it could be point charges, or it could be a charged surface, or whatever it is. And then you have electric fields and you have electric potential. And now we have a way to go between all of these in any direction. So if we're given information about the charge density, and I want to find the electric field, well, there's this expression, and this is what you're going to be using in the tutorial next time when you do the disk, except instead of rho, you'll have sigma here. Okay, but what if I was given the charge density and I wanted to find the potential? Well, we just wrote that down. We just did an example for the case of sigma. So we have this direction. Okay, so given information about charge density, we can find potential electric field. What if we're given information about the electric field? Well, I can find charge density using the differential form of Gauss's law. I could find the electric potential by evaluating this line integral. If I'm given E, I can find the electric field by taking the gradient of the potential, and I can find the charge density using this Poisson's equation. And so we've worked all of that out, and in fact, we've done examples of all those things, except potentially, these two we haven't. Yeah. All right, so this is like a map. Let's see, a map to what's happening. A map to go between the various fundamental quantities in electrostatics. Okay, so the next thing I want to do, how are we doing time-wise? Okay, not bad. Okay. So where are we in the book? We're in 2.3.5, and we're going to talk about boundary conditions. So just looking ahead, we're going to do this boundaries condition stuff, and then we're going to talk about like the energy of a collection of charges, and then we'll talk about electric fields and conductors, and electric potential and conductors. I kind of feel like sort of once we get through chapter 2, which will be by the end of next week, then we've kind of covered all of the stuff that you've seen about electrostatics from a first year class. Of course, we're using more sophisticated math, we're doing harder examples. This boundary condition stuff will be new. But then when we get into chapter 3, that's when we'll really start using some of this new stuff and working with the potential in more sophisticated ways. All right, so the question is, how does the electric field change at the boundary of a object carrying surface charge sigma? All right, like we could imagine we have, like, imagine a uniformly charged maybe for simplicity, let's imagine a spherical shell. So it's a thin spherical shell, and we put charge on the surface, so it has charge density sigma. Like what happens to the electric field as we go from outside the shell across the boundary to inside the shell? And it doesn't have to be a spherical shell, it could be any surface of any shape with some surface charge density sigma. How does the electric field change from one side of that surface to the other? Okay, well, we have the tools to answer that question. I'm going to draw an arbitrarily shaped surface. This is a surface with charge density sigma. And this surface separates two regions of space. Okay, what we're going to do is we're going to apply Gauss's law to the surface. And so that means we're going to have to choose a Gaussian surface. And what I'm going to do is I've tried to draw this thing as if like it's not a flat surface. So the surface can have any arbitrary shape. We're going to choose our Gaussian surface such that it's small enough that we can approximate this surface as being flat in the region that's contained by the Gaussian surface. And our Gaussian surface will have a top and bottom that is parallel to the charged surface. And so what I'll do is I'll try to draw a Gaussian surface. I'm going to make its shape somewhat arbitrary. So let's see, challenge my drawing ability. Okay, so there's a piece above the surface, and then it extends below. And so there it is. Okay, now this top plate is it's parallel to the charged surface. And it has area A. Okay, it also has a normal vector that points outwards. And what we're going to imagine is that we have, some electric field due to this charged sheet. And maybe that electric field is pointing off in some direction like this. Actually, I'm going to put it over here where I have more space. So there's my electric field. When we do Gauss's law, as you know, we're going to have to evaluate this kind of integral where the dA vector is the dA times this n hat thing. And so when I look at my electric field, I can see that I've drawn it in some arbitrary direction. It's going to have a component that is parallel to n hat, and it's going to have a component that's perpendicular. In fact, it's a little weird, but I'm going to call the vector that's parallel to n hat as E perpendicular. I'm calling it E perpendicular because it's perpendicular to the surface that we're thinking about. And then there's going to be a component that is perpendicular to n hat and parallel to the surface. And I'm going to call that E parallel. Okay. The one other piece of information that I'm going to specify is that when I look at the thickness of my Gaussian surface, I'm going to say that that has thickness epsilon. And I'm going to use epsilon to represent some infinitesimal thickness. Okay, good. So when we evaluate this E dot dA, since dA is in the n hat direction, which is perpendicular to the charged surface, only the perpendicular component of E survives. Right, the dot product's just going to get rid of the parallel component. So that means E dot dA is the same thing as E perpendicular times dA. Okay, that's fine. Then if I wanted to evaluate this integral, which is around a closed surface, right, with this little circle here. Well, if we go look at the surface that I chose, I have a top piece, and I have a bottom piece, and I have some side pieces. So, well, in fact, I'll consider the side piece just one strip, like it has a weird shape, but it's one continuous strip. So this would be the integral over the top surface of E dot dA plus the integral over the bottom surface of E dot dA plus the integral over the sides of E dot dA. All right, so we've already said that for the top, this is just going to be E perpendicular dA. What about the bottom? What would we get for the bottom? Yeah, that's right. So if this electric field is going in this direction, and this thing really is infinitesimally thin, then the electric field at the top and bottom is the same. This one's kind of pointing up. The bottom surface would have an n hat pointing down, so the dot product would bring in a negative sign. That's right. So what you're going to get from the bottom surface is minus E perpendicular dA. So we'll specify that this is at the bottom and this is at the top. Okay, now for the sides, we do have like E parallel pointing out here. And so if you did for like some finite thickness, E dot dA for the side surface, that's non-zero. But what we're imagining is that we're very, very close to that charged surface. And when you're very close to the charged surface, this epsilon goes to zero. So there's no area to this strip. And so the flux through that side surface would be zero. Okay. So this one is going to have to be zero in the limit that epsilon goes to zero. And so this is infinitesimally thin Gaussian surface. A different argument to get the same result is that if you truly are very close to a charged surface, let's think about a conductor. So this is maybe specific to conductors, but here's another argument. If you're close to a conductor in equilibrium, what equilibrium means that the charges inside the conductor are not moving. If I had a component of the electric field that was parallel to that charged surface, it would exert forces on the charge at the surface and they would flow in a net direction. And that would violate our assumption of an equilibrium conductor. So for conductors, there could be no E parallel component like I've drawn here. But for insulators, you can do that. So for insulators, we have to rely on this epsilon argument. For conductors, we have a second argument for why that side integral would be zero. Okay, so anyways, that's what we have. And so therefore, it must be the case that the integral of E top perpendicular dA minus the integral of E bottom perpendicular dA. Well, it's Gauss's law, so that has to be equal to Q enclosed over epsilon naught. But what's Q enclosed? If we have a charge per unit area sigma, and this top plate has an area A, how much charge is inside our surface? Sigma A, that's right. But sigma times A is equal to Q enclosed. And I'm going to do one other thing. I'm going to argue that if we make our Gaussian surface small enough, so we've already shrunk the thickness down to 0, but if I make also the area small, then across that area, the electric field strength is not changing. And that means I can factor out the E top and E bottom. Now you might have some wild situation where, you know, there's a huge amount of curvature and a really complicated distribution of charge on some surface. And so the electric field is changing like crazy very rapidly. I could always just pick a value of A sufficiently small that for that piece of surface area, the electric field is approximately constant. And for sufficiently small values of A, we can assume that E perpendicular top or bottom is approximately constant. Okay, so if we do that, then we would say E top perpendicular times the integral of dA, but the integral of dA is just going to be A, minus E bottom perpendicular times the integral of dA, which is just A, is equal to Q enclosed, which is sigma A divided by epsilon naught. And now we can cancel the A's, which is a nice thing, because we just went through this argument like, oh, I can make A smaller and smaller and smaller. Well, it turns out it doesn't matter how small I make the A, I'll always get the similar sort of conclusion that says the difference in the perpendicular components of the electric field at the top and bottom of this charged surface is determined by the charge density divided by some constant. And so there's a sudden discontinuity in the perpendicular component of the electric field when you cross a surface with a surface charge density. So the perpendicular component of E changes abruptly when we cross a boundary with surface charge density sigma. All right. So we also have a parallel component. And so let's see what does that happen. So is there any guesses on what we could do? We used Gauss's law to find the perpendicular component. What else do we have that might help us find the parallel component?
Sure.
Yeah, I mean, I think, is it here? We're going to do this kind of, instead of doing a surface integral, which is not here, I guess Gauss's law in integral form is not written down here, but we have this expression. And in particular, what we're going to do is we're going to integrate around a closed loop. And then when we integrate around a closed loop, we get back to our starting point. And so the change in potential has to be 0. So to see what happens to the E parallel component, or let's say to the parallel component of E. We'll consider E dot dl around a closed loop. So I'll draw our surface again. And our loop is going to be something like this. So we'll go around a loop like so, in a clockwise direction. The dashed lines are below the surface, and then the solid lines are above the surface. And so then we have top parts, we have side parts, and we have a bottom part. We're going to do the same trick as before. We're going to say, let's assume that the length of the side parts is epsilon, and we'll ultimately consider the epsilon goes to 0 limit. Okay, so well, let's see. This time I'll draw my electric field something like this. I'll have an E parallel component, and I'll have a E perpendicular component. Okay, well, we're gonna have to do stuff like E dot dl. Well, for the top side, the way I've drawn it is that E is kind of in the direction of the path integral, so they're both kind of going to the right. So the dot product is going to be positive, and it's going to select the component of E that's parallel to the path. So it selects E parallel. So this is going to be E parallel times dl. And for the bottom, well, everything's more or less the same, except the path now is off to the left, whereas the electric field tends to the right. And so we'll just pick up that minus sign. Here, I have to get my notation right. This is going to be E parallel top, and this will be minus E parallel at the bottom. Then we have dl. And then for the sides, what we're going to do is we're going to say E dot dl is going to go to 0 in the limit that epsilon goes to 0. So we make our loop really have almost no height. It's just we have one that's directly above the surface and one that's directly below the surface, but there's no separation between the two. Okay, so if we do that, then this integral around the path, around the closed path, is going to be the integral of E dot dl for the top part, plus the integral of E dot dl for the bottom part, plus the integral of E dot dl for the two sides. The sides we've already gotten rid of. The top and bottom are these expressions after the dot product. Again, we'll make our loop small enough so that E is approximately constant everywhere along that loop. So we'll factor these out of the integral, and then we'll just have the integrals of dl. And so if we make the length of this loop L, what we would ultimately end up with is E parallel top times L minus E parallel bottom times L. But what's the integral of the electric field dot dl around a closed loop? 0, right? It's a conservative force. So this is a calculation with the work around a closed loop. but the work is path independent, and if our path starts and ends at the same point, we do zero work. Okay, well, that's convenient because now I can divide the L out, and I can say therefore, the parallel components of the electric fields are continuous. There's no change between the parallel components when you cross a surface with charge density sigma. Only the perpendicular component goes through a change. So the parallel components of E is continuous across a charged boundary slash surface. All right, good. How are we doing? 5 minutes. All right. So let's begin our. So in next week's tutorial, we'll come up with some examples for you to work on where you calculate these parallel and perpendicular electric fields crossing boundaries and stuff like that. But sort of one of the last topics, there's two topics that we have left from chapter 2. One is now the kind of energy of a collection of charges, and the other one is electrostatics and conductors. So this is 2.4. This is going to be work and energy. And so we'll just set this up. I'm going to start with the work kinetic energy theorem. Who remembers what is the work kinetic energy theorem? Yeah, that's right. So work is equal to the change in kinetic energy, and work is calculated as F dot dl between 2 points A and B. And so that has to be equal to the change in kinetic energy. All right. For electrostatics, F is equal to Q times the electric field. Okay, so we're going to sub in F is Q times E. And we know that the electrical force is conservative. So what property does a conservative force have besides the work being path independent? It leads to some conservation principle. What is it? Yeah, conservation of specifically of mechanical energy. And mechanical energy is the sum of kinetic and potential. So if that's conserved, that means any change in kinetic energy has to be, there has to be the opposite change in the potential energy. So all I can do is convert some potential energy into kinetic and kinetic back into potential, like so. So conservation of mechanical energy requires that the change in kinetic is equal to minus the change in potential. So this is for conservative forces, the mechanical energy is conserved. Okay, so let's make those changes then. So what we would have is that the integral of F dot dl becomes the integral of QE dot dl is equal to minus the change in potential energy. I'll divide by Q and multiply. Let's divide by minus Q. That's one way to do it. Let's divide by minus Q. And so we'd have the integral of E dot dl is equal to delta U divided by Q. And let me put my integration limits in. Oh, okay. So that's fine. But the first thing we did today was show that this was equal to the change in electric potential. We kind of did it in two ways. You could either do the argument that we did right at the beginning, or you could say, by the fundamental theorem for gradients, this has to be the change in potential. So this was minus the potential at B minus potential at A. So minus the integral of E dot dl gave us the change in potential. So E dot dl gives us minus the change in potential. Oh, okay, so fair enough. That means therefore, I'm missing, I forgot to bring this negative sign, right? Perfect, good. So I'm gonna cancel those negative signs now. And so therefore, the change in potential is equivalent to the change in potential energy per unit charge. So this is a relationship between the electric potential and the electric potential energy. And so it's unfortunate that the names of these two quantities are so similar. It leads to confusion, but you have to distinguish between electric potential or voltage and potential energy measured in joules. They're obviously related, and they're related just by this factor of Q, but in the language, you have to be careful whether you're talking about electric potential as in a volt or potential energy as in something measured in joules. Okay, so that's where we'll leave it for today. What we'll do next week, there's no class on Monday. So on Wednesday, we will finish up this energy discussion. We're gonna try to talk about how much energy does it cost to assemble some distribution of charge. And then we'll talk about conductors and electrostatics. All right. Have a good weekend if I don't see you tomorrow in 331.